Okay, so now that we've been able to use Lewis structures, Vesper theory, and differences in electronegativities to determine the overall polarity of molecules, we're going to now see how we can apply the molecular polarity to some of the interactions between molecules. And we refer to generally the forces of attraction between molecules. We refer to those forces of attractions as intermolecular forces, right? So these are attractive forces between neighboring molecules. IMFs, I'm sorry, intermolecular forces are often abbreviated, so also known as IMFs, right, for intermolecular IMF. So we'll use that abbreviation throughout our course. Collectively, we also refer to intermolecular forces as van der Waals forces, or sometimes you'll see this being written as VDW for van der Waals forces. And there are three types that we're going to see. So we have three types of intermolecular forces, or IMFs. And we'll list them in order of increasing strength. We have what are known as dispersion forces, or London's forces, London dispersion forces. Okay, and these are the weakest of the IMFs. We have dipole attractions. And then we also have hydrogen bonding. Which we abbreviate as H bonding. And this is the strongest out of the three types of IMFs. Okay, so let's take a look at each of these in turn. We'll start with the weakest ones, which are the dispersion forces, or the London dispersion forces. And again, both of those terms are used interchangeably. So what is a dispersion force? Well, first of all, you find these between all molecules. Okay, so these are found between all species, all chemical species. Whether it's a polar molecule, non-polar molecule, doesn't matter. This is always present. So everything is going to have a dispersion force between it and something else. You can think of a dispersion force as being the most, even though it's found between all chemical species, it is going to have a larger effect. So it has a larger or greater effect in non-polar molecules. Okay, so if you can imagine, if this is a non-polar molecule that we have here, okay, so there is no separation of charge within the molecule. There's no overall net dipole. Well, over the course of time, because electrons are free to move around, at some point in time, the electrons may temporarily spend more time around one end of the molecule than the other end of the molecule. And in that case, what we've introduced here is what's known as an instantaneous or a fleeting dipole. Okay, it's not permanent, it's just temporary. And it happens just based on the movement of electrons that are zipping around. At any point in time, you may have electrons spending more time around one end of the molecule than the other. And what that can do, it can then induce or cause temporary dipoles in neighboring molecules. Okay, and that's what the dispersion force of attraction is. It's just these temporary instantaneous dipoles that just happen because there are electrons present, and they randomly will spend more time around one end of the molecule than the other. We have these fleeting dipoles that are produced that then induce dipoles in neighboring molecules as well. Okay, these are the weakest. All right, these are the weakest forces of attraction. So the weakest of the intermolecular forces. Okay, they're not very strong at all. And again, like I said, they're going to predominate in our non-polar molecules. And what we tend to find is the size of the molecule will have an impact um, on the strength of those dispersion forces, and as a result, the subsequent physical characteristics such as the boiling point. All right, so I will use a boiling point to help to explain the differences in IMFs. So if something has a high boiling point, this means that there are strong intermolecular forces holding the molecules together, right? If you think about it, a strong intermolecular force means that the molecules are held really, really strongly together. So it takes more energy to separate those molecules so they go into the gas phase, for instance. Okay, and that's all that means. Stronger intermolecular force, higher the boiling point. That's the general trend that you want to think about. So stronger IMF, higher the boiling point. Okay, so if we make a comparison between these molecules here, these are our halogens. Okay, they're all diatomic, and they're all made up of F2, for example, is made up of two Fs. Okay, Cl2 is made up of two Cls. Br2 made up of two Brs, etc. So these are obviously going to be non-polar molecules because there's no difference in electronegativity between any of the atoms here in these. So the only difference between them, right, these are all non-polar. The only difference here is their molar masses, right? They're different in sizes. And what we see is that the larger size, the one with the greater molar mass, has a higher boiling point. And that then would mean if the boiling point for iodine, for example, is 184 degrees Celsius, at room temperature, which is around 20 degrees C, this thing is going to be a solid. Okay, so it is important to consider the sizes of molecules when they are similar in everything else. So for example, the F2, all the halogens, they're all non-polar. We can now attribute any differences in boiling points to the differences in molar masses, for instance. Okay, something like fluorine has a boiling point of negative 188 degrees Celsius. So at 20 degrees Celsius, it has already boiled. It's in the gas phase, so it's going to be a gas. And that's a general trend, not just within the non-polar molecules, but when we get to the polar molecules as well, right? If everything else is the same, we can look at the difference in molar mass to compare boiling points and the sizes or the strength of the intermolecular forces. So everything, all molecules will have dispersion forces between them. Where they become important when they actually do influence boiling points, for instance, are when we're dealing with non-polar molecules, because that's the only type of intermolecular force you'll find in non-polar molecules, right? So let's write that down. So non-polar molecules will only have dispersion forces between them. So let's move on to the next stronger intermolecular force, which are dipole-dipole interactions or our dipole-dipole attractions. Sometimes you see that term being used. Okay, so these are attractive forces that act between polar molecules. Remember, polar molecules have a net dipole. In other words, there's one end of the molecule that's slightly positive. So delta plus, and the other end is slightly negative or delta minus. Okay, and these are permanent dipoles that we're talking about. It's not instantaneous as in the case of the dispersion forces. So these will if you have these molecules that have permanent dipoles, right, we can imagine the red end being negative, the blue ends being positive, that we can predict just based on what we know about positive attracting negative, we can predict that the slightly negative ends of one molecule, so here, for instance, will be attracted towards a slightly positive end of another, right? So that's just based on opposites attracting, and that's exactly what is going to happen in dipole-dipole interactions. These are stronger than the dispersion forces. Okay, and we find them in polar molecules, right? So we find them in. So if we were to list the intermolecular forces between polar molecules, there are two types. Okay, we're going to have dispersion forces because those are present between everything. So you always list those first. And then now a polar molecule then will have these dipole attractions. Okay, so if we compare again, several of these uh, of these molecules, and these have similar molecular masses, so their sizes are very similar. The only difference between these are their polarities, right? So we can measure that based on their dipole moment, right? So we talked about this earlier. The larger the dipole moment, the more polar the molecule is. Okay, so something like propane, which is actually non-polar, because all it's made up of are non-polar bonds, carbon-hydrogen bonds, carbon-carbon bonds, right? Very, very low dipole moment, non-polar, has a very low boiling point, very low boiling point. And if you compare that to something like acetonitrile, okay, which has this chemical formula, the carbon-nitrogen bond is a very polar bond, and that influences the polarity of the molecule. Okay, so these down here are polar, and the polarity increases in this general direction as we list them because the dipole moment increases. What we find is that the boiling point increases as well, right? So this here has a very high boiling point because it has a very large dipole moment, which means we're going to have very strong dipole-dipole interactions or dipole-dipole attractions between molecules of acetonitrile compared to the very weak dispersion forces between propane molecules. So dipole-dipole, those are the second strongest of the intermolecular forces. The third is called hydrogen bonding, which we often abbreviate as H bonding. And you can probably guess what needs to be present for hydrogen bonding to exist. Okay, so hydrogen needs to be present. And not only must it be present, it also needs to be covalently bonded to a very electronegative element, such as a nitrogen, an oxygen, or a fluorine. Okay, so you can think of a hydrogen bond as sort of a very very strong type of dipole-dipole interaction, but we classify it specifically as a hydrogen bond. Okay, so two criteria need to be satisfied. You need to have hydrogen present, and that hydrogen needs to be covalently bonded to an O, or covalently bonded to an N, or covalently bonded to an F, and then whatever else is connected to the O, whatever else is connected to the N. And in the case of F, there's only one bond to fluorine. So in the case of, and if you think of, the one molecule that we know a lot about, water, H2O, right? Now we can see that yes, there's hydrogen present, so there's a possibility of hydrogen bonding. Is the H connected to an O, an N, or F? Yes, it's connected to an O. So right away, we know that hydrogen bonding is going to be present. So if there's another water molecule floating around, like over here, for instance, let's say there's one right next door. There's an O, and there's two H's. Okay, we know that the O is going to be slightly negative because it's more electronegative than the H's. H's are going to be slightly positive. And we have that same thing happening in neighboring water molecules. Okay, what can happen is I'm going to separate these here just by outlining the different molecules that we have. Okay, the H from one can be attracted to the O to a neighboring water molecule, right? Again, positive attracting negative, that attraction there between molecules, right? That is what the hydrogen bond is. Okay, it's not a covalent bond. Okay, it's not the OH bond, this bond here, where there's a line between them. It's not that one. It's just an attraction between different or neighboring water molecules. So it's not the OH bond. And this is happening in all of the positions in water, right? You can imagine this water molecule at the bottom, that is going to be um, participating in hydrogen bonds to another water molecule, like so. Okay, have a hydrogen bond there, and so on and so forth. So because water now has not just dipole, I'm sorry, not just dispersion forces, but it's got now this really strong hydrogen bonding. What we find is that water has an anomalously high um, boiling point compared to similar types of molecules. So for instance, if you compare the hydride of the group 6 elements, so H2O versus H2S, H2SE, H2TE, you see there's generally, as we go down the group, an increase in the boiling point. However, where we would expect water to be, which would be, if we extrapolate this line, maybe down here is where we would expect it. That's your expected boiling point for H2O. Instead, it is way up here, right? Why is the boiling point so high? Okay, this is due to hydrogen bonding. Okay, it takes a lot more energy to separate these water molecules from each other because you have the really, really strong hydrogen bonds between them. And we see that happening in the case of the other um, molecules on this chart as well, right? So if you compare, for instance, the hydrogen halides, okay, we'll try to highlight these on our chart. The hydrogen halides are in blue. Okay, hydrogen iodide, whoops, hydrogen iodide over here. Let me erase this really quick. Hydrogen iodide, hydrogen bromide, hydrogen chloride. Again, if we extrapolate this, we would expect hydrogen fluoride, okay, to be somewhere around here, but instead it is way up there, right? Why is there this difference? Hydrogen bonding can explain that difference, okay? If we look at the group 5 hydrides, again, comparing uh, antimony hydride, arsenic hydride, uh, phosphorus trihydride, we would expect NH3 to be somewhere down there, over here, is where it's expected. However, it's up there. The reason why it's higher than expected is because of the hydrogen bond, in this case, between ammonia and H3 molecules. Because the ammonia does have hydrogen that's covalently bonded uh, to an N. Okay, so the presence of hydrogen bonding is very important, not just in the case of water, but you also find it in these other examples that we talked about. There are also uh, ramifications for living organisms. Okay, so for instance, hydrogen bonding, right? We find those in, for example, organic and biochemical molecules. And if you think about Things like carbohydrates that have lots of oxygen-hydrogen bonds, OH bonds in them. They're going to be chock full of hydrogen bonds. We have things like proteins. Proteins are held together sometimes. Their shapes are held together by hydrogen bonding. And probably the most important example of where hydrogen bonding um, is found in biochemical molecules is in your nucleic acids. So things like DNA and RNA, right? The double helix of DNA, if you've ever seen a picture of a double helix, it's actually held together by hydrogen bonding. So it's very, very, very important, not just in these simple molecules like water, which is the basis for life on our planet, but also in the case of DNA, the thing that contains your genes that make you who you are, right? Those molecules are held together by hydrogen bonding as well. Okay, so we've seen the three types of van der Waals, collectively known as van der Waals forces or intermolecular forces or IMFs. There's another type of force that we find, force of attraction between uh, polar molecules and ions that we call ion dipole interactions or ion dipole attractions. And as the name suggests, these are attractions between these are attractions between ions, okay, so things that are positive or negative, and also polar molecules, so molecules that have uh, slightly positive, sorry, slightly positive and slightly negative regions. Okay, so for instance, if you look at the case of, this is a water molecule that we have here, H2O. Okay, there's our H's and there's the O, and these are connected in this bent shape, right? We know that the hydrogens are going to be slightly positive and the O is going to be slightly negative. Hydrogen slightly positive, O is going to be slightly negative. If we have an ion, like a cation, for instance, floating around, like a sodium ion, we would predict that it is going to be attracted to the negative end, the slightly negative end of the oxygen, of the water molecule, right? That just makes intuitive sense. Opposites attract. Similarly, if we have a higher charge cation, like a Mg2+, we would expect it to be oriented close to the slightly negative end, which is the oxygen of the water molecule. In this case, there is a stronger attraction because the magnitude of the charge here is greater. So, and it's greater specifically than that of the 1+ charge and the Na plus. And we saw this trend when we looked at lattice energies early on. It's the same idea. Now the attraction is happening between the ion and a dipole rather than between an ion and another ion. By the same token, we can imagine if there is a negative ion, such as a chloride, a Cl minus, right, we would expect that to be attracted towards the slightly positive end of the water molecule, like the H's, right? And that's another example of an ion dipole attraction as well. And that is, and we'll talk about this when we get to our solutions later on, but this is the reason why, for instance, sodium chloride, NaCl is able to dissolve in water because it breaks apart into its ions that are then attracted to the water molecules in a very predictable fashion. So we've seen dispersion forces, we've seen dipole-dipole attractions, we've seen hydrogen bonding. Those are intermolecular forces. And then we have our ion-dipole interactions. Those are attractions between molecules, polar molecules, and ions, things that have full positive or negative charges.